Good day, fellow civil engineering students. In this video, we are going to tackle about the chapter 3 of the provided reference book. So, chapter 3 is entitled as Abstractions from Precipitation. So, chief components of abstractions from precipitations are necessary in the analysis of various hydrologic situations. And there are 20 topics or content in this chapter. Sections 3.1, which is the introduction, to 3.11, potential evapotranspiration over India. This discussed about the various aspects of evaporation from water bodies and evapotranspiration from a basin. While in sections 3.12, actual evapotranspiration, and 3.13, interception, it is all about the interception and depression storages which act as sluices in the production of runoff. And sections 3.14, depression storage, to section 3.19, classification of infiltration capacities, it discussed about the infiltration process, which is a major obstruction from precipitation and an important process in groundwater recharge and in increasing soil moisture storage. And last topic of this chapter, which is found in sections 3.20, infiltration indices. In sections 3.1, introduction, sections 3.2, evaporation process, sections 3.3, evaporimeters, and section 3.4, empirical evaporation equations, I will be the one who will discuss that topic, and the rest will be discussed by my fellow reporters. So before we proceed to the main discussion of this report, first we must look back the previous discussion from the first group, which they tackle about precipitation. So I have here a brief description or definition of precipitation. So denotes all forms of water that reach the earth from atmosphere. So usual forms of precipitations are rainfall, snowfall, hail, frost, and dew. Now, section 3.11, introduction. So, in engineering, hydrology runoff due to a storm event is often the major subject of study. All obstructions from precipitation, those due to evaporation, transpiration, infiltration, surface detention, and storage, are considered as losses in the production of runoff. Evaporation from the bodies and soil masses together with transpiration from vegetation is termed evapotranspiration. And this evapotranspiration will be further discussed by my fellow reporter. So I will be the one. So in this video, talking more on evaporation. So I have a short video about evaporation, and please do watch this so that we do have an idea what is evaporation all about.
Evaporation. In this video, we are going to learn about evaporation. Evaporation is the process by which water gets converted from liquid form to a vapor form. Evaporation from the oceans accounts for 80% of the water delivered as precipitation, with the balance occurring on land, inland waters, and plant surfaces. Let us do a small activity. Place a beaker containing water on a stove. Let the water boil. If you continue to heat the water, it turns into steam and evaporates. Add some spoons of salt to water another beaker and stir it well. The salt gets dissolved. Now heat the salt solution. The water gets evaporated, leaving the salt behind. Seawater contains salt mixed in it. Common salt is one amongst them. When seawater is allowed to stand in shallow pits, water gets heated by sunlight and slowly turns into water vapor through evaporation. In a few days, leaving the salts behind, water evaporates completely. Common salt is then obtained from this mixture of salts by further purification.
Okay, that is evaporation. So, to further know about the evaporation process, let's now discuss. So, evaporation is the process in which a liquid changes to the gaseous state at the free surface below the boiling point through the transfer of heat energy. Evaporation is a cooling process in that the latent heat of vaporization at about 585 cal over G of evaporated water must be provided by the water body. So of example where evaporation process takes place are in the bodies of water and boiling water. The molecules of water are in constant motion with a wide range of instantaneous velocities. An addition of heat causes this range and average speed to increase. When some molecules possess sufficient kinetic energy, they may cross over the water surface. Similarly, the atmosphere in the immediate neighborhood of the water surface contains water molecules within the water vapor in motion, and some of them may penetrate the water surface. The net escape of water molecules from the liquid state to the gaseous state constitutes evaporation. So there is a rate of evaporation. So rate of evaporation is dependent on the following. First, the vapor pressures at the water surface and air above, air and water temperatures, wind speed, atmospheric pressure, and quality of water. Lastly, the size of the water body. So vapor pressure. The rate of evaporation is proportional to the difference between the saturation vapor pressure at the water temperature, which is denoted as E sub W, and the actual vapor pressure in the air, which is denoted as E sub A. So John Dalton, 1802, who first recognized the law of evaporation. So here is the Dalton's law of evaporation, which is E sub L is equal to C multiplied by E sub W minus E sub A, where E sub L is the rate of evaporation, so millimeter per day, and C is constant. E sub W is equal to the saturation vapor at the water temperature, so millimeter of mercury, and E sub A is equal to the actual vapor pressure in the air, so millimeter of mercury. Next is the temperature. So rate of evaporation is dependent on temperature. So the rate of evaporation increases with an increase in the water temperature. Regarding air temperature, although there is a general increase in the evaporation rate, with the increasing temperature, a high correlation between evaporation rate and air temperature does not exist. Third, wind. Wind aids in removing the evaporated water vapor from the zone of evaporation and consequently creates greater scope for evaporation. The rate of evaporation increases with the wind speed up to a critical speed beyond which any further increase in the wind speed has no influence on the evaporation rate. This critical wind speed value is a function of the size of the water surface. For large bodies, high-speed turbulent winds are needed to cause maximum rate of evaporation. Fourth, atmospheric pressure. So a decrease in the barometer pressure as in high altitude increases evaporation. Soluble salts. When a solute is dissolved in water, the vapor pressure of the solution is less than that the pure water and hence causes reduction in the rate evaporation. The reduction in evaporation approximately corresponds to the percentage increase in the specific gravity. For example, under identical conditions, evaporation from seawater is about 2 to 3% less than that from the fresh water. Lastly, heat storage in water bodies. So deep water bodies have more heat storage than shallow ones. A deep lake may store radiation energy received in summer and release it in winter, causing less evaporation in summer and more evaporation in winter compared to a shallow lake exposed to a similar situation. However, the effect of heat storage is essentially to change the seasonal evaporation rates, and the annual evaporation rate is seldom affected. So, because there is, we know that estimation is important, or estimation of evaporation is important, especially sa mga lugar nga nihit og tubig. So, estimation of evaporation is utmost importance in many hydrologic problems associated with planning and operation of reservoir and irrigation systems. The exact measurement of evaporation from a large body of water is indeed one of the most difficult tasks. In arid zones, this estimation is particularly important to conserve the scarce water resources. So there are three methods in solving or in finding the estimated evaporation. First, we have evaporimeter data. Second, empirical evaporation equations and analytical methods. So, first, we are going to discuss about evaporimeter data. So, evaporimeters are water-containing pans which are exposed to the atmosphere and the loss of water by evaporation measured in them at regular intervals. So, meteorological data such as humidity, wind movement, air and water temperatures, and precipitations are also noted along the evaporation measurement. So, usa sa gamiton sa pagkuha sa estimation of evaporation or pila in the bodies of water pila ang ning evaporate nga tubig, usa sa gamiton nga or method is using evaporimeters. So there are four types of evaporimeters: the Class A evaporation pan, the ISI standard pan, the Colorado Sanken pan, and US Geological Survey floating pan. First, we have the Class A evaporation pan. So, it is a standard pan of 1,210 millimeter in diameter and 255 millimeter depth used by the U.S. Weather Bureau and is known as Class A land pan. The depth of water is maintained between 18 cm to 20 cm. The pan is normally made out of unpainted galvanized iron sheet. Mono metal is used where corrosion is a problem. So the pan is placed on a wooden platform of 15 cm height above the ground to allow the free circulation of air below the pan. So evaporation measurements are made by measuring the depth of water with a hook gauge in a sealing well. Okay, here is a picture of Class A evaporation pan, an actual picture. Next is the ISI standard pan, which this pan evaporimeter is specified in the IS. Its code is 5973 to 1970. So also known as a modified Class A pan. Consists of a pan of 1,220 millimeter in diameter with 255 millimeter of depth. The pan is made of copper sheet of 0.9 millimeter thickness, tinned inside and painted outside. A fixed pointed gauge indicates the level of water. A calibrated cylindrical measure is used to add or remove water, maintaining the water level in the uh, in the pan to fixed mark. The top of the pan is covered fully with a hexagonal wire netting of galvanized iron to protect the water in the pan from birds. Further, the presence of a wire mesh makes the water temperature more uniform during day and night. The evaporation from this pan is found to be less by about 14% compared to that from unscreened pan. So the pan is placed over a square wooden platform of 1,225 millimeter width and 100 millimeter height to enable circulation of air underneath the pan. So, mo ni ang ijang picture. Okay. Next is the Colorado sunken pan. So this pan has a 920 millimeter square and 460 millimeter deep. Is made up of unpainted galvanized iron sheet and bored into the ground within 100 millimeter of the top. So the chief advantage of the sunken pan is that radiation and aerodynamic characteristics are similar to those of the lake. However, it has a following disadvantages. So first is difficult to detect leaks, and extra care is needed to keep the surrounding area free from tall grass, dust, and etc. And lastly, expensive to install. The next kind of pan is the U.S. Geological Survey floating pan. With a view to simulate the characteristics of a large body of water, this square pan, it is 900 millimeter side and 450 millimeter depth, is supported by drum floats in the middle of a raft, which is 4.25 meters by 4.87 meters, set afloat in a lake. So the water level in the pan is kept at the same level as the lake, leaving a rim of 75 millimeter. Diagonal baffles provided in the pan reduce the surging in the pan due to wave action. Its high cost of installation, its disadvantage is it's a high cost of installation and maintenance together with the difficulty involved in performing measurements. So those are the four types of evaporimeters: the Class A evaporation, ISI standard pan, Colorado sunken pan, and US Geological Survey floating pan. Now, let's proceed to the pan coefficient P. So, evaporation pans are not exact models of large reservoir and have the following principal drawbacks. So, the ratio of the amount of evaporation from a large body of water to that measured in an evaporation pan. So again, evaporation pans are not exact models of large reservoir and have the following principal drawbacks. So the following are the principal drawbacks. First, heat storing capacity and heat transfer from the sides and bottom. Second, height of the rim in an evaporation pan affects the wind action. Third, the heat transfer characteristics of the pan material is different from that of the reservoir. So, the heat storing capacity and heat transfer from the sides and bottom, the sunken pan and floating pan aim to reduce this deficiency. As a result of this factor, the evaporation from a pan depends to a certain extent on its size. While a pan of 3-meter diameter is known to give a value which is about the same as from the neighboring large lake, a pan of size 1 meter diameter indicates about 20% excess of the evaporation than that of the 3-meter diameter pan. And height of the rim in evaporation pan affects the wind action. Also, it casts a shadow of variable magnitude over the water surface. And lastly, again, the heat transfer characteristic of the pan material is different from that of the reservoir. So, in the view of the evaporation observed from a pan has to be corrected to get the evaporation from a lake under similar climatic and exposure conditions. Thus, a coefficient is introduced as lake evaporation is equal to C sub P multiplied by the pan evaporation, in which C sub P is equal to the pan coefficient. So the values of C sub P in use for different pans are given in table 3.1. So here is the table 3.1, values of pan coefficient C sub P. So section number 1, types of pan. Class A land pan, average value 0.70, ranges from 0.60 to 0.80. Second, ISI pan, also known as modified class A, average value is 0.8 and range is 0.65 to 1.10. Third is the Colorado sunken pan, average value is 0.78 to 0. And ranges from 0.75 to 0.86. Lastly, USGS floating pan, average value is 0.80 and ranges from 0.70 to 0.82. So, there are evaporation stations ug asa dapat ipamutang ang evaporimeters. So, the WMO, or known as the World Meteorological Organization, recommends the minimum network of the evaporimeter stations as below. So, in arid zones, one station for every 30,000 kilometers squared, and in humid temperature climates, one station for every 50,000 kilometers squared, and in cold regions, one station for every 100,000 kilometers squared. So, typical hydrometeorological station contains ordinary rain gauge, recording rain gauge, Stevenson box with a maximum and minimum thermometer, and dry and wet bulb thermometers, wind thermometer, wind direction indicator, sunshine recorder, thermohydrograph, and lastly, again, especially the pan evaporimeter. Now that we're done discussing evaporimeter, let's now proceed to another topic, the empirical evaporation equation. So, empirical evaporation equations, it is also a method on estimating water evaporation. So, what is empirical evaporation equation? So, mo ni siya. A large number of empirical equations are available to estimate lake evaporation using commonly available meteorological data. So, most formula are based on Dalton type equation and can be expressed in the general form. So, this is the Dalton type equation. So, E sub L is equal to K multiplied by F times U multiplied with E sub W minus E sub A, where EL is equal to the lake evaporation per millimeter per day, E sub W saturation of vapor pressure at the water surface temperature, millimeter of mercury, E sub A actual vapor pressure of the overlying air at a specified height, just using millimeter of mercury again, and F multiplied by U is the wind speed correction function, and K is the coefficient. So E sub A is measured at the same height at which wind speed or U is measured. So there are two commonly used empirical evaporation formula. These are Mayer's formula and Rower's formula. So in Mayer's formula, where E sub L is equal to K sub M multiplied by E sub W minus E sub A multiplied by 1 plus U sub 9 over 16. So E sub L is the lake evaporation, millimeters per day. E sub W is the saturation vapor pressure at the water surface temperature, millimeter of mercury. E sub A, actual vapor pressure of the overlying air at a specified height, millimeter of mercury. And U sub 9 is equal to the monthly mean wind velocity, or kilometer per hour, at a height of 9 meters above the ground. And K sub M is equal to the coefficient accounting for other factors. Remember that we should use, when using the coefficient accounting for, coefficient accounting, 0.36 is used for large deep waters and 0.50 for small shallow lakes. We will understand it. Makasabot to tayo nga na when we are going to solve those example problems. But now, let's discuss first the Rower's formula. So, this formula is considered a correction for the effect of pressure in addition to wind speed effect, and is given by E sub L is equal to 0.771 multiplied by 1.465 minus 0.000732 P sub A, and is multiplied to 0.44 plus 0.0733 U sub 0, and again it is multiplied with E sub W minus E sub A. So P over A means barometric pressure, so it is denoted as millimeter of mercury, and U sub 0 mean wind velocity in kilometer per hour at the ground level. So taking as the wind velocity at 0.6 meter height above the ground. So E sub L, E sub W, and E sub A are mentioned earlier. So, hibaw na taon sa to. So now, however, in view of the various limitations of the formula, they can at best be expected to give an approximate magnitude of the evaporation. So, in using empirical equations, the saturated vapor pressure at a given temperature, just denoted again, the E sub W, is found from the table of E sub W, Vs temperature in uh, degrees Celsius, such as table 3.3. So table 3.3, you can find it or you can view it on the provided reference book found on page 72. Okay. So often, the wind velocity data would be available at an elevation other than that needed in particular equation. However, it is known that in the lower part of the atmosphere, up to a height of about 500 meters above the ground level, the wind velocity can be assumed to follow the 1/7 power law as U sub h is equal to C multiplied by h raised to the power of 1/7, where U sub h is equal to the wind velocity, and h height above the ground, and C is constant. Note that this equation can be used to determine the velocity at any desired level if U sub h is known. So now that we're done discussing about the empirical equations, let's try an example problem. So an example problem, a reservoir with a surface area of 250 hectares had the following average values of the climate parameters during a week. So the water temperature is equal to 20 degrees Celsius. Relative humidity is equal to 40%. Wind velocity is at 1 meter above the ground surface, which is equal to 16 km per hour. So the question here is estimate the average daily evaporation from the lake using Mayer's formula. So here is the solution. So it is given that our Km is equal to 0.36. Again, Km denotes as the coefficient accounting for various other factors, and E sub W is equal to 20 degrees Celsius. So, nganong tingatanga, this amaning 17.54 millimeter for mercury. So, again, ingon dito nga ang E sub W is the saturated vapor pressure at the water surface temperature in millimeter of mercury. Ingon dito nga, ato makitaan sa table 3.3. So, naatay 20 degrees Celsius. So, equivalent nga saturation vapor pressure ni kay 17.54. That's how we come up with kani. 17.54 millimeter for mercury. And E sub A is the actual vapor pressure over lying air at a specified height of the millimeter in mercury. So, given nga na ay 40%, so convert it, which becomes 0.4%. Then multiplied by 17.54, muna dire, so is equal to 7.2 millimeter of mercury. In U sub 9, 16 kilometer multiplied by 9 raised to the power of 1/7 is equal to 21.9 kilometer per hour. So, we can now get, so na-typo ko dire, sorry. That is 16 kilometer per hour. Okay. So, mo na ni ang iyang solution. So, kay naa naman tay mga value ani sa formula sa Mayer's formula, ato na si Jang i-substitute. So, 0.36 kay, okay, nagamit na itag 0.36 kay Again, ayon there is a Mayer's formula nga 0.36 for large deep water. So mo to itong gamit. So, So, mo na 0.36 multiplied by 17.54 millimeter of mercury minus 7.02 and multiplied by 1 plus 21.9 over 16, we can get 8.97 millimeter per day. That's the answer of the first question. Next problem is an ISI standard evaporation pan at the site indicated a pan coefficient of 0.80 on the basis of calibration against controlled water budgeting method. If this pan indicated an evaporation of 72 millimeter in the week under question, so first is estimate the accuracy of Mayer's method relative to the pan evaporation measurements. Second, also estimate the volume of water evaporated from the lake in that week. So here are the solutions. So first, the daily evaporation as per pan evaporimeter. 72, ganun tinatawag. This naman nagikan ang 72. So 72 is mo na ang given nga indicated evaporation sa usa ka semana. So mo nang 72 over 7 multiplied by 0.8, which is the evaporation site indicated of the pan coefficient. Mo na. 0.80. So, is equal to 8.23 millimeters. So, the error by Mayer's formula. So, ang 8.23, mo ni ang natong nakuha dito sa first problem. First, mo ni 8.23. Atong nakuha nga daily evaporation of a pan. So, ang 8.97, mo to ang atong nakuha or nakuha nga answer sa previous na to nga problem, which is mo ni 8.97 millimeter per day. Minus, aron makuha na to ang error sa Mayer's formula. So, hence, Mayer's method overestimates the evaporation to the relative to the pan. So, it is negative 0.74. So, percentage overestimation by Mayer's formula is equal to 0.74, which is the error by Mayer's formula, mone, and divided by the daily evaporation, which is 8.23, multiplied by 100, so makuha na to nga 9%. So, muna ang estimate the accuracy of Mayer's method relative to the pan evaporation measurements. Next is we get considering the pan measurements as the basis, volume of water evaporated from the lake in 7 days so is equal to 7 multiplied by 8.23 millimeter divided by 1,000 times 250. Gisa man ang 250. Moto nga gimension nga land area sa first province, 250 hectares. So, muna, multiply by 10 raised to the power 4, we can get 144,025 cubic meter. Munang answer. So, that is the estimated volume of water evaporated from the lake in that week. So, that is all. That is the end of my report. Thank you for listening and goodbye.